How to choose a helium miner antenna. Keep it simple, keep it real. Now, over the last couple of months and really recent weeks, it came to light there's a lot of activity and a lot of interest in LoRaWAN, helium mining, LongFi, any of those technologies, and specifically with the antennas and antenna upgrades that might be available. So there's a whole new community of people suddenly looking and making inquiry about antennas, and I had a look online, and there's also, I'd say, a bit of questionable information being shared or statements being made online. So I just wanted to take this opportunity to get into that mindset and also just present some of the antenna fundamentals and basics that we apply at RF Shop in our 4G and 5G world, also in the Wi-Fi world. Just make sure that the fundamentals and the basics are well understood for people that want to go for helium mining, and that's what I'm going to do. So yeah, of course, that's what I'm going to do. So the questions that currently seems to be quite relevant on the internet, or not relevant, prevalent on the internet, is one is, what is the best mini helium miner antenna? So the short answer to that is there is no best helium antenna. The thing here is you need to look at quality. So if you look for bad quality antenna, then you're going to have a problem. So if I refer back to my 4G, 5G experience, what you see if you go on the typical online stores, eBay or Amazon, nothing against the platform, it's just sometimes the people that sell there really make nonsense statements about the antenna performance and antenna gain. So like 40 or 50 dBi gain, it's not possible, but then they have a small antenna. So don't buy cheap as you can get. That's the big thing I would say. But the best antenna needs to be looked at for your specific application. So the question then becomes, how do I choose what antenna is best for my setup? So you definitely have to look what your setup is. And in this video, I really want to go through a few scenarios and just kind of explain the different parameters that an antenna has and how that could apply for you, and how you need to make the best, how you can make the best decisions for your antenna. And then a question we get, not just for helium mining, but a question you can get for any type of application. We hear this a lot, is how far will my antenna go? How far will my helium miner reach with this antenna? It's a bit of a difficult question, and probably a bit easier to answer with helium mining, because you know the frequency band is like, say, 915 or 928 megahertz, or overseas it's somewhere 860 megahertz or so forth. So you know at least what frequency is being operated at. So you can do some calculations using a specific type of antenna to see what is the losses over the air from point A to point B. You do need to take into account, though, what is the actual performance of the receiving end as well. So there's a lot of math involved, but you can get a better number, but it's not an easy one. And you also need to take into account what's obstructions between you and the other point. So I'll just, well, maybe not in this video, but subsequently we can talk about that as we go through different videos as well. Now, one important thing, it's not just an antenna, but to me it's just another antenna of an antenna type we've already been selling. So now I just realize we need to emphasize the antennas are also applicable for LoRaWAN, for helium mining, for all sorts of IoT applications. So we have the listings on RF Shop website, rfshop.com.au, where we now have 4 different types of antennas, which is all Omni antenna, a 3, 6, 8 and a 9 dBi Omni. I have it there on my table as well. So there's a 3 dBi, there's the 6 dBi, and then behind me, that long one, let me just show you, is what you would expect from the 9 dBi type of antenna. So you can see that's humongous, but it's available, can be done. So we obviously need to present that as an option. So in the kits that we have on our website, we combine it with cables. So we have 5 and 10 meter cables. What is very important from RF Shop's perspective is coaxial cable is a customizable item, and for us we do a lot of custom coaxial cables. So you can go to our custom cable builder, you can reach out to RF Shop, and you can ask for a specific cable length, and if you want different connectors than what we have in the kit, always just ask. We definitely have those options, where SMA and M-type connectors are quite standard for us to deal with, also the cable types. But as far as RF Shop is concerned, we have this channel, we're running this channel for all sorts of wireless technologies. So please stay connected. Like what we're doing, if you specifically think the topic of helium mining is of interest and is also important to you, and if you think we can talk more about some of the topics we're going to discuss today, feel free to subscribe. Actually, no, don't feel free to subscribe. please subscribe to our channel and click that bell so you'll see what updates there are when they come your way. Now, the topic for today is really an overview of all the things, I guess, that is relevant that I think is maybe not quite that clear. And each of these topics can actually be spent, I can spend much more time on them than what I'm going to do today, because each of them deserve a whole discussion. And I mean, I've been building this channel for almost 2 years now, trying to address each of these differently and then with different modems and so forth in the 4G world. I'm going to translate that same conversation to helium mining and the IoT as well. So the first one is gain and radiation pattern. So that's a loaded gun almost, or loaded question. Size really matters. The first thing is, I have seen some comments online where people say there's a small antenna that has high values, or big antennas that have equal number of gain or performance numbers. Look at the source of where it comes from. An antenna at 900 megahertz needs to be, for 2 dBi, which is a dipole length, say that's that. A dipole length is about 16.5 centimeters long, because that's a half wave at that frequency. Those antennas will be about 2 dB gain. So if you double that size, you can get 3 dB more gain. That's how it works. That's the physics behind it. So if you say about 33 centimeters or a little bit longer, you should get in the order of 5 dBi gain. Then double that, which means 4 times 16.5 centimeters, or let's say 70 centimeters, 80 centimeters. That's when you get to the number that's about 8 dBi gain. So it's not an absolute statement that I'm making here, but that's the order of magnitude. And if something is totally out of whack, if somebody says there's an antenna that's 8 dBi gain and it works at 900 megahertz, but it's only 30 centimeters long, no, not going to happen. Not going to happen. So the next thing, which is an obvious one, is basically a directional versus an omnidirectional antenna. So it seems the most logical application for helium mining is to have an omni antenna, because everybody wants to have presence in the middle of a specific cell, so everybody around them will know that they are who they are. But say you live on the coast, you only have people living on that side, or say you are behind a big hill behind you. So it's kind of pointless to go for an omni antenna in those cases, and you just want to know, I want everything there. I might as well get all my visibility and all the exposure in that direction. Now, this comes into the real issue that I have seen, and where I just want to start with, is the radiation pattern of an antenna. Typically, you see an omni antenna such as this, and people show a donut type shape. So they have this, and I have used a balloon as well in the past to illustrate how this works. So there's a balloon shape around the antenna. That balloon shape shows, as I have this picture here in front of you with the 2 circles. Basically, you have to see it as all around. So no matter how you turn this thing, you see the same shape. The problem with that, and what I have now seen and learned, is there seems to be an assumption that it's like throwing a ball. It goes up and it comes down. So the radio waves from this thing, it radiates up and it comes down a bit later. That's not how it works. The reason for that donut is we actually, as an antenna engineering community, we use a polar plot. Polar plot means we look at a point and we just look all around. So, well, at that angle, that's how strong it is. That angle, that's how much it is. At the end, it turns out to look like a donut. But the reality of how an antenna works is more like a ray of light. And that's why I have that picture on the right, and that's what I'm going to use going forward. That you have an antenna, from me to the point far away. And this is with cell phones the same, it's with 4G the same, it's with Wi-Fi exactly the same. From me to there is a straight line. Over the distance and the speed of light that we're talking about here, the speed that the radio waves are moving, it's not going to drop down, it's not going to go loop over. So you can't go, this is a high building, there's a really low antenna, low gain antenna, and it's going to loop over and come down again. It doesn't work like that, it goes straight. So that's so important to realize, that if there's something between you and the object in front of you, or repeat, if there's something between you and the object you want to talk about, and there's something in between, it's not going to happen. You need to do something to get out of that line so that the tree or the building is no longer in the way. That's it, what I want to say about that. So now just want to quickly run through different gain values to explain the differences there. So first one, as I mentioned, this is basically a low gain omni antenna. It does that, it goes not too far, but it goes quite high. So you have nice view up and down. if you have people around you, there's people you want to cover, so you look at that number of people. So let's say on one side I have their building. So if this is next to a high building or a higher spread building, you will get coverage through the whole building. For instance, you have to be specific about the setup there, and you can see that you have reach across the whole thing. Then on the other side, where it's just, this is now all around. On the other side, there are people, there are recipients you want to see. The guy who's furthest away, who is totally on the edge of the screen, he's not going to get anything. The one who's close to the edge, close to the point where there actually is a transition from maybe there's a signal to, nah, this is too far away, question mark. Maybe he gets it, maybe he doesn't. And then people in the field of view, of course, they're happy. No challenges there. The next one is a medium gain. Saying 6 dB is a medium gain, just to compare to what a low gain would be. Say this is an antenna like this one. This is now the 6 dB example, or 6 dB actually specific for the helium mining antenna. You can see it's a little bit less, so the elevation exposure is a little bit less. So you don't see that much anymore, so you can't see that high and that low. You see a little bit less, but you can see further. So now your visibility is a little bit further. How that translates into actual having people there. In the building side, you're not going to have the coverage to the top and to the bottom, but you have a stronger signal. As you can see, it actually goes a little bit into the building. There's a stronger signal, so it may go in a little bit. On the other side, where you have little people and little recipients, the guy that's midway, he gets it. The guy below still gets it because the beam is still broad enough. The guy who was a bit on the outskirts, so a bit on the high end, he's gone. You can't see him, and it still doesn't reach the guy that's furthest away. The last example, which is really if you go for the big one, like that big one that I have here behind me, say a 9 dBi Omni antenna, quite a narrow beam, so it's really focused on the horizon. So you really say, that's it, I want to go, I skim through the horizon, but I want to go as far as possible to the horizon and see everything that's available over there. That's a good thing. You get far away. So there you can see the guy who was the furthest away on the screen. Now he has a tick. He's happy. The guy who was a little bit closer, he's in the line. He's happy. The guy who was on top, so on the top of the screen, he's gone. He can't see anything. And the guy who is somewhat in the line, but he's a little bit on the edge, I don't know if he's going to get it or not. You'll have to see. On the building side, the picture gets quite interesting. And this is where it gets important for me to explain how this works. You of course get nice penetration into the building in that line, so you kind of have to, you cut into it, and those floors probably will get the signal. But the guys at the top of a high-rise building and quite at the bottom, if it goes much lower, they won't see you because they're out of that signal. I added another person on the screen as well on the left who's behind the building. He's not going to see you. He would not have seen you if any of the antennas were used. So it's not a case of it could have jumped over and back down again. He would never have seen anything. So I introduced that little guy there. Now, the other topic is outdoor versus indoors. Now, I have seen comments saying fiberglass is better, don't go for the plastic ones. That's not what it's all about. Fiberglass is more robust against the outdoor elements. So if you are in a snow country, sure, that'll help. If you are in a warm country like Australia, that'll help. If it rains a lot, that'll help. If it's plastic, it's probably also not waterproof. So the sun might chew it up, so it's not going to last that long. You might get water ingress, then the whole thing will deteriorate. But fundamentally, what's in there is what's important, and it might be the same thing that's in there for a plastic antenna or a rubber antenna or this fiberglass antenna. It's just how they protect it so that it can be placed outside or inside. Now, nothing stops you from putting an outdoor antenna on the inside. It's going to work exactly the same. Also doesn't stop you from putting a plastic one on the outside if it's maybe protected and then doesn't get any rain or doesn't get any direct sunlight or something like that. Again, size. I mean, it's impractical to put that type of antenna that's 1.6 meter long outside, inside. I mean, it's just going to be the whole floor long. So it's just practicalities. It's not possible. And mechanics, well, this one, for instance, it's robust. So this one, you've seen that earlier. You could put this, you can mount this properly. For the indoor ones, they're more delicate, and you have a magnetic base. So nice, you could put it on a table, maybe close to a window, and then you'll have something that radiates. So that's really what it's about, outdoor versus indoors. More mechanical questions, more environmental issues. It had nothing to do with the electronics. If somebody has a reliable data sheet, again, I'm going to say reliable, and it says this is a 6 dBi Omni antenna. If it's a plastic one or if it's a fiberglass one, it'll be 6 dB. It's just where do you place this thing. Next question is antenna placement. Now, this is one that I think deserves more than just one video, but I'm going to just have a bit of a summary presentation here. So antenna, I'm going to assume somebody lives in the city and he lives in a building, in a block of flats or some high-rise building. If you put it on the outside, just outside your window, it's almost like you have a directional antenna, because it's going to be there and you're going to have a lot of coverage forward. And to the back, inside at the same floors, you probably will get some coverage there. But don't expect that the whole building will get a signal, and don't expect that people on the other side of the same building will get much of a signal either. So the building is what we call a massive attenuator, a block. It just stops things from really going through, so it stops penetration. Now 900 megahertz is not too bad actually, so you will get some movement through. So that's the awesome thing about this frequency. It does give you a lot of, well, it's very forgiving, so it does give you a lot of penetration through, but it's going to reduce the signal significantly. Now another example is the same setup, but basically now you put the antenna a little bit higher, so you put it on the roof or above. What I wanted to highlight, if this is the scenario, is you still have a potential problem where it gets shielded, so your signal is still blocked by corners. So that's why I said forget about this up and over kind of mindset. It's a straight line. It needs to cut straight through. So that guy, that little gentleman or lady that I put behind the building, she's still not going to see that signal because she's still shielded by the building itself. The last one is if you can go a little bit higher, you can really get the antenna to be clear of any obstruction. You could see the object. You have line of sight. And we call it line of sight. Now, I should have used that word earlier. Line of sight means you can see where you want to go. If you have human line of sight, if the light goes from one point to the other one, the radio wave is also going to travel the same path, and you could see, well, this is going to reach that point. If it's strong enough, that's not a question, but it's going to at least have the directionality and reach there. And see, now in this case, everybody's happy. Everybody has a signal. Now, what I have seen as well, people put awesome antennas on the inside, and I understand, and I have heard that that's sometimes just the limit of what is practically possible. So you may not have the luxury of drilling a hole on the outside, or being able to screw an antenna mount onto the side of a building, or have something put on the roof. You may only have a rental unit, for instance, then you put it on the inside. It is what it is in that case, but you just need to be mindful that you can't have a full omni performance, and that's why I said we do need to think maybe directional antennas is an option here, because what's physically going to happen is you get the signal, and so through a window or something, it will send your will create coverage on one side, but to the back where there's a lot of walls, there's a lot of obstructions, there might be cabinets, there might be a lot of metalworks, it's just going to cause issues to the back. So that's a big issue. And when you place an antenna somewhere, place it somewhere intelligent. Don't place it behind the fridge where the fridge is between you and the window, obviously. Put it somewhere where it's close to the window so it actually goes out. I mean, it goes without saying, but if there are millions of users out there, you're going to see some stuff that well, just think where you place your antenna. Let's just skip it to that. Now, cable quality and cable losses. This is really a thing where RF Shop is where it keeps us so busy. We have so many cables we do, but I just want to talk about this, and I'll just run through 4 popular cables for 50 ohm. 50 ohm is the same for LoRaWAN as we use for 4G, 5G, so it's similar to application. So very basic summary: low loss, good quality will give you the maximum range. You don't lose any of your signal, not any. You lose very little of your signal in the cable from your modem or your router or your miner to your antenna. What happens if you have bad quality cable? Nothing changes except for, have a look at this, the peak point. So the shape change, the antenna radiation pattern remains the same, everything remains the same. It's all just weaker. It's all just, you just don't get to reach, which is probably the worst outcome there is, because if you had a low gain antenna, at least you had better coverage. Now you have a high gain antenna, which is still just this slight elevation. It's only that, but it only reaches up to here, doesn't reach up to there anymore. So it's kind of the worst of the worst to use bad cables. So I always say antenna is really important, but the cable is as important, if not almost more important, because you can mess it all up with a bad cable. Just want to run through them quickly. There's a few examples. So what I have seen online, and the easy ones to use, is RG316 or pink colored cable. It's really thin, it's very flexible. It's the most lossy as well, about 1 dB per meter at 1 gigahertz. Now, I just in my quick search this morning when I prepared for the video, I didn't find data sheets for 900 megahertz. I thought it's close enough. It proves the point. Every meter of that cable, you will lose 1 dB, and it will lose 1 dB of gain from your antenna, basically. That's really a bad thing. So what we do when we use for other applications at work, GPS or Wi-Fi or 4G, we say no longer than 1 meter, never. So here it's even more so. If you really want your miner to have the maximum coverage so that you can get the best connectivity to other miners and devices, you definitely don't want to go for this cable much more than you need. Then the one that gets really useful is the LMR 195 or equivalent. We have CLF 195, can get LMR 195 as well, but CLF is just another brand using exactly the same antenna specification and performance. It's the size of RG58, so you're looking about between 5 and 6 millimeter total diameter. It's still very flexible, but the loss is about 0.36 dB per meter at 900 megahertz. So basically it's a third. So it's really much better than RG316 for cable lengths. However, if you go to the next one, which is LMR 240, well, there's other cables in between as well, but these are just very common ones that you can just get from most places just straight. So CLF 240, it's more flexible. No, not more. It's a little bit less flexible than LMR 195, but it's still very flexible, very easy to handle, but the losses are even better. So now you're at 0.5 dB, which is like 4 times better than the RG316. And typically in the 4G world, up to 10 meters, we are quite happy to recommend this one because it's practical, it's very useful. It gets low loss as far as the performance is concerned, but practically it's still mechanically an awesome cable to use. Then the last one, which seems to be very popular, and I do understand why, but it's not always practical for people, is the LMR 400 or CLF 400 cable. It's 10 millimeter. It's quite hard to work with. So short cable, 1 or 2 meter cables, it actually gets a little bit awkward. So I wouldn't specifically use it if it was me, but obviously it's up to a customer to decide what they want to use. But the losses there is 0.14 dB at per meter at 900 megahertz. So it's definitely way less than the other ones, and that's an awesome cable. That's all I actually have to say about that. It's turning out to be a much longer video than I expected or anticipated, but hey, it's a big topic. It's an important topic, and now we can break it down into these 4 topics and spend more on it. Hopefully we will get our own miners soon, and then we can play with these antennas, see the results in actual life as well. But for now, if you buy an antenna, think about these things. If you choose a cable, choose the right cable. Don't just say, this looks okay, we'll use this. Make sure that you use good quality cable. And if you want any of these antennas from RF Shop, just visit our website, rfshop.com.au, and we will help you with the antenna, and we will guide you through the correct cable selection as well. Thanks for watching, and see you on the next video. Bye-bye.